So, Professor Awata Sensei from Nagoya, and he will talk on introduction to the Q-deformed Virasoro algebra. So please start.
Thank you very much. I'd like to thank the organizers to make an opportunity to talk this nice conference. My title is Introduction to the Q-deformed Virasoro algebra. This is completely some review and introduction for this subject. So the first part is first introduction. The Virasoro algebra is very famous. It appears as a symmetry of string theory, or more precisely, the dual resonance model of hadron amplitude. But in 1984, there is big breakthrough by Belavin, Polyakov, Zamolodchikov. That is, they found this algebra applied to the two-dimensional critical phenomena, for example, Ising model or Potts model or RSS model. And they found a so-called BPZ equation. That is a key point of this first revolution of Virasoro algebra or conformal field theory. And another important revolution is made by Adley Tachikawa, Gayot Tachikawa, 2009. They find the relation between Virasoro algebra and gauge theory, four-dimensional super Yamil theory. That is so-called AZT correspondence. That is second big revolution. And there is also third relation. This Virasoro algebra has a relation with one-dimensional many-body quantum mechanics, so-called Carl-Sutherland model. So Virasoro algebra is very important, and there is many relation with many physics. So today I introduce this Q deformation of this story. I just deformed of these story like this. For example, this I will define that this Q deformed Virasoro algebra, but they relate many similar in the Q=1 case. So first, string theory should be changed to M theory. M theory is there is another dimension that is circle, and its circle's radius r is related to this parameter q. Q equals essentially exponential of this radius r. And on the right-hand side is a one prime relation that two-dimensional critical phenomena should be changed to non-critical phenomena. That is, a critical phenomena means the last part. Critical phenomena means this is relation with is only for a special temperature, but for any temperature, this Q-Virasoro algebra relate with this critical non-critical phenomena for any temperature. And another relation is ADT relation, 2 prime. That is, it was four-dimensional. But if we deformed, then that will be five-dimensional. Five-dimensional gauge theory. Dimension is up. So, and another relation is three dash. That is, it was changed to relativistic many-body quantum system. Q equal 1 case, that is only usual many body quantum mechanics. But that deformed case change to relativistic quantum mechanics. I mean, this appears new parameter speed of light. So in this talk, I just defined this bilateral algebra and see what is relation 1, 2, 3, and next defined this Q bilateral algebra and see what is 1 prime, 2 prime, and 3 prime. So I start from the usual bilateral case. So bilateral algebra, that is a key symmetry of conformal field theory, or CFT. And it's bilateral generator or bilateral operator. I wrote Ln, n is any integers, and commutation relation is like this. This commutation relation is usual. A, B bracket is usual AB minus BA. This Ln and Lm's commutation relation is almost Lie algebra, but plus this second term appears. The delta is usual Kronecker delta. If Ln and L minus n, Ln and L minus n, L is, in that case, this second term appears, and this C is important number, that is central charge. This parameterize this theory. This is the definition of bilateral algebra. Bilateral algebra is generated by this bilateral operators. And I make some remark. First remark is these three I times I is root of minus 1. I times L minus 1 minus L, and I times L1 is nothing but SU2 generators. I mean, angular momentum. They, if there's, in this case, L0, in this type of angular momentum relation. And second remark is C equal 1 and 0 case, central charge vanish case. That is this operator realize conformal transformation or local scale transformation. In that case, this generator Ln written by differential operator, Z is some complex number, and the n plus 1 times derivative of Z. So this differential operator, it's easy to check that this differential operator satisfies above the bilateral relation without the second term. So in this case, C equals 0 case, this transformation is usual conformal transformation. They preserve the angle of figures. So this is a classical symmetry of string theory. So that is the one reason that this bilateral operator appears in string theory. So this is a definition of bilateral operators, and using that, we need primary operators. We need another operators to see the relation with physics. The important operator is primary operators. I wrote it's phi, h, z. H and z is complex number, and the definition is like this. A commutation relation with L and phi, this primary operator, is linear in this primary operator, but times Gn or n plus 1 times h plus differential operator, differential. operator, Z round Z. This H is important number named scale dimension. And to see the physics or critical phenomena, in the two-dimensional critical phenomena, there is important operators. For example, in the Ising case, the central charge C should be 1/2, and this scale dimension is 1/16 or 1/2. 1/2 case, this is corresponding to energy operator, and 1/16 case, this operator corresponds to spin operator, and so on. In the criticalism case, C should be 7/10, and H should be these 5 values. 3-state spot case, C should be 4/5, and so on. So this central charge C and scale dimension has some nice relation with the operators in critical phenomena. And to see the relation with critical phenomena, we need introduce the we need correlation function. So we need to introduce vacuum in the usual way. Vacuum, this bracket 0 defined by that vanish by Ln n positive. Bracket vacuum should be vanished by n negative mode. And also we need some relation constraint on this primary operators similarly, but using the vacuum, and we define the correlation functions like this. That is sandwich this vacuum ket and vacuum bra sandwich and this product of primary operators. That is a correlation functions Virasoro algebra, but this is this correlation function easily computed. For example, n is number of primary operators. N equal 1, 2, 3 case. This is almost trivial. It's very easy to calculate. And first non-trivial case is n equal because they have that is conformal transformation. So they have SL2 SL2Z symmetry. So we can fix 3 of the this Zi was the 1 to infinity. Z1 is 1, 0. Z2 is 1, and Z3 is infinity. So we can fix this 3 variable Z to any value, for example, 1, 0, infinity. So n equal 1 to 3 case is almost trivial to calculate. And so first non-trivial case is n equal 4. In that case, there is one variable, Z4, does not eliminate. So the n equal 4 is first non-trivial case. They depend on one variables, but it is easy to calculate in this time because of there is 2 ways to calculate. The first is using differential equation that is found by Belavin, Porekov, Zamolodchikov in 1984. That is, in this case, second order with regular singular points. That means this equation is the usual Fission differential equation, or just a hypergeometric differential equation. So using this, we can easy to calculate, or solution is just a hypergeometric function. The second way to using free boson realization. But anyway, so this differential equation is the important first revolution of this CFT. And second relation, this is first relation with Virasoro and physics or critical phenomena. The second relation with Virasoro and physics is this is the same correlation function is nothing but the partition function of 4D n equal to SU2 super Yamil's theory. That is Adlai, Guyot, Tachika found very amazing relation. That is the second relation. Virasoro correlation function is related with super Yamil's theory. And third relation is, to see the third relation, we need a Virasoro state. That means start not vacuum. This is also vacuum, but start with the vacuum-like state H defined by Ln n positive vanish and L0 eigenvalue is H. That is the definition of this state, bracket state H. And acting on this ket state, the Virasoro generator, positive mode vanish, so we need to apply negative mode. But the first negative mode L-1, second one is L-2 or L-1, L-1. Third level in L-3 or L-2, L-1, or L-1, 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 or like that. In the fourth level, we need 5 independent state. Anyway, there are many kind of state. But in this state, there is, if this value H or scaling dimension H or central charge C is very special value, then this Virasoro state, these states become dependent. These states usually, in general, this is independent, but in some special value of C or H, they are become dependent, and they appear singular state, this chi, that defined by which is inside this state and vanish by positive mode of Fn. Figure this singular vector is inside this states, space of states, and this H is vanished by positive mode and generated negative mode is survive. But inside this space of states, there is some singular state. They vanish in the positive mode, and also that means usually this Virasoro state, if we act the second is L-1 to L1, then they return to the highest one, H. So we can easily to go down and go up. It's easily to go down and up, but if there exists such dangerous state, we can go into this their space, but we cannot back again. So these states are some dangerous state. But anyway, that dangerous state has relation with has nice relation with the third physics system. The singular state can be mapped to excited state of Karjero-Sutherland model. This is found by Mimachi Yamada. And this is inclusion mapping. But if we generalize this Virasoro algebra to some another algebra, Wn algebra, then Wn should be many, 1, 2, 3, every n. But then the singular vector state of Wn algebra has 1 to 1 correspond to excited state of Karjero-Sutherland model. Well, anyway, so this is a third relation. So I show the 1, 2, 3 relations. So next I show its Q deformation. So I show this 1, 2, 3. So next I show this Q deforms them. 1 prime, 2 prime, 3 prime. Before that, I should define this Q bilateral algebra. So definition is this Q bilateral algebra or Q deformed CFT is generated by this generator, Q bilateral operator. I wrote it Tn. N is also integer. And commutation relation is like this. Tn and Tm's commutation relation is like this. This is a little bit complicated. This is right-hand side is not linear. This is t times t minus t times t and sum of all n. And f is, before that, there is 3 parameters. Q, T, P is complex number. And T equals Q times beta, and beta is almost a central charge. And P is defined by Q over T. So independent parameter is 2, Q and T, or any 2 parameters independent. And the coefficient F, structure function F is defined by this Fx. That Fx is defined by exponential of something, and its expansion coefficient is Fm. So this is not Lie algebra. Second term is the usual central term. This is not Lie algebra, but they form a closed algebra, and they have very nice structure. So this is called Q bilateral operators. They generate Q bilateral algebra. And we show some remark. The first relation with usual bilateral operator. Let Q goes equal to exponential h bar, and take h bar goes to 0, then Q goes to 1. Then this Q bilateral generator goes to bilateral operator with central charge C equal 1 minus 6 times beta minus 1 times 1 minus 1 over beta. This beta is nothing but correspond to the center. And how to this? If we introduce the generating function of this generator Tn by Tz, defined by sum of all integers n and Tn times z to the minus n, then if we expand in h bar, then first the second term in h square appears Lz. Lz is the generating function of usual bilateral Ln. So this is not trivial, but the bilateral generator appears in h bar expansion. Second remark, this relation is written by this defining relation is rewritten by this generating function t by in this form. F is this function f times t minus t times f, the parameter z and w exchange. Then the right hand side we have this delta is delta function. this delta x defined by the sum of every xn, and they satisfy, that is a multiplicative delta function. This satisfies any function if we multiply any function fx, then the x can be reduced to 1. Usual delta function is this x goes to 0, but this is not that. This is multiplicative delta function, so x goes to 1. Anyway, we can rewrite this definition in this way. So this is the definition of Q-bilateral algebra. And to see the relation with physics, we also need the primary operators. But to define primary operators, it is easy to, it's convenient to use free boson realization. This Q-bilateral generator T is realized by free boson. The free boson operator is defined, that I wrote it's n is integer, and Q. The commutation relation is usually a commutation relation with an and am is Kronecker delta n plus m. And this coefficient is not important. The coefficient is strange, but it's not important. It's just a convention. And another an computation relation with an and q is also Kronecker delta. And then using this free boson, the Q-bilateral operator, this Tz, can be written in this form. Tz is lambda plus times lambda plus lambda minus. Then lambda plus minus is defined by, in this form, exponential boson type relation. And this dot is usually normal ordering. That is, positive mode should go to the right. For example, A3 and A minus 3 should be, A3 should be on the right, to move to the right. And A0 and Q is, A0 should go to the right. That is the definition of this normal ordering. Anyway, in this way, the Q-bilateral generator, this T, can be realized by this free boson operator. And using this to see the relation with physics, we need to define primary operator. I wrote it phi tilde. Q equal 1 case, I wrote phi. So in the generic Q case, I wrote tilde. That is also written by, that is also exponential boson type operators. But they have scaling dimension h and a little bit complicated expression. This gamma is t to the gamma is h. So this primary operator is the relation between bilateral operator is a little bit complicated. For example, that they satisfy these kind of relation, but a little bit complicated, but they have some nice relation. Anyway, using this primary operator, phi tilde, we see the relation between the physics. So next I see the Q deformation of this relation 1, 2, 3. I mean, this relation was non-critical phenomena and gauge theory and relativistic many-body quantum mechanics. So that is like this. First, I show this 1 prime, 2 prime, 3 prime. The first, the relation with non-critical phenomena. If we consider the correlation function of this primary operator by tilde, actually we need we need also another operator, screening current we need, but anyway, the correlation function of this primary operator is nothing but the correlation function of ABF model. That is always Andre Baxter Forrester found the some non-critical phenomena. So that is done by Lukyanov Pugai 96. And another relation is that is 1 prime. Another relation is that is Q-deformed AGT correspondence. That is 4-point case. That product of this primary operators, 4 primary operators, and sandwiched by vacuum, then that is nothing but the partition function of 5-dimensional n equal to S2 super Yang-Mills. That is a Q deformation of ADT correspondence. That is conjectured by with Yamada-san 09, and that is conceptually proved, showed by with Feigin-Shiraishi-san that its partition function is nothing but the correlation function of some other algebra, Rin-Iohara algebra. And using the Mickey duality, this relation 2 prime is proved. But that Mickey duality is explicitly shown by the Fukuda, Okubo, Shiraishi-san in 19. So this relation is explicitly proved. That is second relation, 2 prime relation. So the third relation is relation with singular state. There is also similarly singular state in this Q-Virasoro algebra, and they have nice involution to the excited state of. Oh, sorry, this is my this is not cultural model. This is Reisner's model. This is misprint. This is not cultural state. This is Reisner's model. That is relativistic version of cultural Sutherland model. That is inclusion. And if we generalize this Virasoro algebra to WM algebra, then this inclusion goes to isometry. One-to-one correspondence. Historically, using this relation 3 prime, we found that using this, I expect this, using this relation, we found this Q-Virasoro generators. That is historically. Anyway, this is third relation. And there is another relation. I mean, up to now, this BPG equation is missing. The BPG equation is Q deformation of this BPG equation is very difficult problem because because Virasoro algebra is Hopf algebra, but Hopf algebra means they act on is easy to act on tensor space, but this Q Virasoro algebra is not Hopf algebra. It's not easy to act on tensor product. So that is one reason this BPZ equation, Q deformed BPZ equation does not found, or maybe geometric picture. To realize, to produce BPZ equation, we need some geometric picture of Virasoro algebra that is conformal transformation. But in the Q deformed case, we don't have some geometrical meaning. So that is maybe another reason. But recently, so 2021, the Shamil Shakirov proposed this Q deformed BPZ equation. That is the last relation. That is a little bit complicated, but in this kind of style. Q deformed BPZ equation proposed by Shakirov is like this. He considered this 5-point function, 5 product of this primary operators, H0, H1, and H4, and 3 of them fixed to 0, 1, infinity. So there are 2 parameters, x1 and x2 survive. And one of scaling dimension h is fixed to special value of t. Then if h is t, then this h is t, then this denominator and the numerator cancel. So that is very h equal t or q is very special value. But if anyway, we can choose q, but in this note, write it t. So t or q is very special scaling dimension. If we choose this special value, then they satisfy nice relation. This kind of nice relation, but very complicated. But this is they satisfy depend on 2 parameter x1, x2. But the relations right hand side, that is 1 over x1 and 1 over x2. The left hand side x1 and x2, or with some shift. And phi is this function, and theta is the differential operator, and dot is normal ordering. That differential operator theta goes to the right. Anyway, this means with some connection type relation with x and 1 over x with some shift. So it's a very some complicated equation, but Shakirov proposed in this type of pure BPZ equation, and we show with Shakirov, Hasegawa-san, Okawa-san, and Kano-san, and Yamada-san, and Shirai-san. We show this is we prove this relation for S2 case. Right. In that proof, we also found that this Shakirov's equation in the special value of this H case, this Shakirov's equation reduced to Q case equation. That is a equation for not Virasoro, but affine real algebras correlation function. Correlation function of affine Q deformed real algebra satisfy the Q case equation, but they reduce to, they include that relation, Q case equation. So that is the key point of our proof. Anyway, that is the Q deformation of 1, 2, 3. So time is up. So thank you. This is the end of my story talk. Thank you very much.
Thank you, Awata sensei. Is there any question or comment from Nagoya?
Thank you for interesting talk. I have one question. You say that Q-plus algebra don't have a geometric interpretation, but Shakirov-san.
Yeah, Shakirov.
Shakirov have QBPZ equation. So is it possible in future Q-plus algebra have geometric interpretation in future? It's hopeless problem?
That is an interesting question, but I don't know. So Shakirov's approach is not geometrical. So, but anyway, geometrical interpretation is still open. And our proof is also using QKZ equation, so it's not geometrical. So I don't know some geometrical meaning of this Virasoro algebra. Virasoro case, that is usual, conformal symmetry, but Virasoro case, sorry, I don't know. And it's not still, it's still open question. Interesting question.
Okay, thank you.
Another question or comment? ありませんか? How about online from Zoom? So then let's thank Awata sensei again.
Thank you very much.
Thank you very much. The next talk will start on schedule. Shu-san, hello.
Hello?
Yeah, I can see your face. Yeah. So please share the screen.
So I share screen now or at 20.
Yeah, I can. That we can see it in your desktop and.
Okay, so I start at 20 or?
Yeah, wait. Just talk will. Let's start at 20 minutes. At
Okay.
20. Yeah.
So let's start the second talk. The speaker is Ronjesh Shu-san from Westlake University. The title is Two Morita Equivalent Condensable Algebras and Domain Walls into the Topological Orders. So please start.
Okay, so thanks for the organizers. I'm gonna talk about the two Morita equivalent condensable algebras and gap domain walls in 2D topological orders. And this is based on this work collaborated with Oliver Xiang. And he is a PhD student at the Chinese University of Hong Kong. So a little bit primer. So loosely speaking, a 2D topological order can be described by a unitary modular tensor category denoted by this curly C here. And some 2D condensation process may happen in C, in which it would create a new topological order described by the category of local A modules in C. And it is controlled by this so-called condensable algebra A here. And anyons that are confined from going to a condensed phase would form a 1D gap domain wall described by the fusion category CA. There are usually many 2D condensable algebras in a topological order. So a natural question is that for what kind of like 2D condensable algebras, say A1, A2, their condensed phase would be the same. And this is equivalent to ask how to classify the two Morita equivalent condensable algebras. And it turns out that this question is related to the gap domain wall between the original phase and the condensed phase, which is classified by the so-called 1D condensation. And that is, we can also have a 1D condensable algebra B here in a category CA, and the condensed phase, the category of BB bimodules in CA, 1-to-1 correspond to the gap domain walls between C and C local. But in order to classify the two Morita equivalent condensable algebras, we also need to consider the invertible domain walls that are classified by the group of graded autoequivalents. But in the condensed phase, we should distinguish two kinds of invertible domain walls. One comes from the original phase. Yeah, and another one is induced from the algebra automorphism of the 2D condensable algebra drawn in A1 here. And actually, the second one does not affect the gap domain wall in C. So if we like close this gap domain wall CA2, we find that this 5 alpha is observed into this CA1 here. So we denote this first saturation by A1, two Morita equivalent to A2, with a small phi here. So this small phi serves as an interchange of anyons between the equivalent condensed phases. So all gap domain walls can be classified by this triple A1, A2, and phi here, in the sense that if we completely close this part, they correspond to a category of BB bimodule in C. So now we know that a 1D condensable algebra B, 1-to-1 correspond to the triple A1, A2, and phi. But one should ask, what is the exact relation between the 1D condensable algebra B and the 2D condensable algebra A? And the answer is centered. So we prove that we can exhaust all two Morita equivalent pairs 2D condensable algebras by taking the left and right centers of the 1D condensable algebra B. Yeah, so I didn't give the exact definition of an algebraic center here, but a 2D condensable algebra is a indecomposable separable commutative algebra. So you can imagine that you add the 1D condensable algebra with some commutative restriction from the left or right box. For example, A1 here, if you map to the wall from this direction, it should be the same as you map it and fuse from the bottom and do a half braiding here. So I will give a physical example right below. And since this is a 1-to-1 correspondence, we also have like any gap domain wall within a topological order can be open. So this, more precisely, that is any if this gap domain wall is indecomposable, it can be opened to contain an inner part that is a condensed phase, and possibly with a phi here. And this can be generalized to any two topological order that are weight equivalent. So let us give an Tori-code model example. So I suppose you know what is a Tori-code. So the local Hilbert space here is a complex number squared, and we define two local operators, AV and BP. So AV is a product of four poly X matrices acting on this adjacent edge, and BP is the product of four poly Z matrices. So here is the lattice realizations of the 1D condensable algebras B locally. And by condensing them, by doing a 1D condensation of these sets, we got the sex gap boundaries in the Tori-code model. And this 1 plus F serves as an interchange between E and M. Okay, so note that the relative position between A and B cannot be interchanged since E and M has a non-trivial half braiding here. So we have an example to show why A and B can have this 1D condensable algebra of direct sum 1 EMF. Since we can add a local trap to the original Hamiltonian, and then the new ground state subset is forced for degenerate, which can be distinguished by the eigenvalues of A and B. And if A equals 1, B equals 1, it is the original ground state subset, so it generates 1. And if A equals minus 1, B equals 1, we have E, and for A equals 1, B equals minus 1, we have M, and for A and B both minus 1, we have F. So here we draw the process of 1D condensation. So you can see we have duplicate this local configuration along line here. And if we remove them, we got this gap domain wall with 1D condensation. So it is described by the category of B5 by modules in a Tori-code model. So the process of taking the left and right center is to expand this 1D condensable algebra to the left and right bulk directly. So and find which subalgebra commutes with B trivially. So for example, if we instead have like 1 plus E here, then it can be expanded to the left or right bulks freely. So its left and right centers are just itself. But here for B5, we see that the left center, we can expand like 1 plus E to the left center. And if we do a half braiding this way, it's trivial, but so it's left center, but it cannot cross this gap, this configuration, since we have a non-trivial braiding beta EM equals minus identity by our definition. And similarly, we have the right center as 1 plus M. So indeed, if we do a 2D condensation using this 1 plus E and 1 plus M, we got the rough boundary for this VAC-Z2 and the smooth boundary for the RAP-Z2. And this bimodule category is equivalent to VAC-Z2 box times RAP-Z2. So the 1D condensation is parallel to 2D condensation in the sense that if we take the left and right centers and do the condensation like horizontally, they generate the same gap boundary. And here is a Hamiltonian of the gap domain wall. So this slide performs the exact calculation of the right and left centers. And this is a mathematical definition of a left center. So as the center is lies in the same modulated set category as the 1D condensable algebra, we can just consider its commutative subalgebras, which are two, like 1 plus E and 1 plus M. And you can see that if we plug into 1 plus E, this diagram commutes since beta ME equals identity. However, if we plug into 1 plus M, this diagram does not commute since beta EM here is minus identity. So 1 plus E is the left center of B5. And similarly, we have 1 plus M as the right center of B5. So 1 plus E and 1 plus M are two-meriter equivalent. And the above slide is just a translation of this mathematical definition. And moreover, the two-meriter equivalent condensable algebras can also be classified by Lagrangian algebras. L in the double fold of C, also denoted by the Drinfeld center of C. So the fusing then folding process would lead to a gapped boundary of the double fold of this topological order. And by a Lagrangian algebra, we mean the maximal condensable algebra that condenses a vacuum. So the Lagrangian algebra one-to-one correspond to the gap boundaries. And moreover, we have the Lagrangian algebra equals to the fourth center of the 1D condensable algebra. So recall that the left and right centers are two-meriter equivalent. So another way to get the two-meriter equivalent pairs is to intersect the Lagrangian algebra as the fourth center with its left and right components. Yeah, and this theorem states this arrow here. So it is that for this triple, for the gap domain wall given by this triple, it one-to-one correspond to the gap boundaries given by the Lagrangian algebra here. So back to the torical model example, we have 6 Lagrangian algebras in the double fold of TC. And if we intersect them with TC or the time reversal of TC, we get these two-meriter equivalent pairs. Like for this one, we got one two-meriter equivalent to 1 with a phi here. And for this one, we got 1 plus E, two-meriter equivalent to 1 plus M. So there are two two-meriter equivalent classes in total. One contains 1 plus E, 1 plus M, and another one contains just 1. Yeah, and we can also start from this 1D condensable algebra here and taking their left and right centers to get the same result. And the domain walls shown here are just the inner part here is the condensation condensed phase for this two-meriter equivalent pairs. So if we count the invertible domain walls, there are 6 gap domain walls in the torical model in total. So this page shows our main results, which is this triangle here. So we give a complete interplay between the two-meriter equivalent condensable algebras, one-meriter class of 1D condensable algebras, and Lagrangian algebras. And some of the arrows here was discussed by some of the papers here. So we have unified them into a full trinity. And by taking their module categories, we can translate these algebraic descriptions into the domain wall descriptions. So you can start from any corner here and get the other two. So some other examples. A classical example here is the Hitayu quantum double model described by the Drinfeld center of VecG. And David once classifies the 2D condensable algebras in this category using the subgroup H of G and the normal subgroup F of H. So we can use the trinity to play around. And this table is the Z2 topological order. That I will skip this page. And this table shows the S3 topological order. Yeah. And an interesting phenomenon here is that there are 4 Z3 invertible domain wall, four invertible domain walls in the Z3 topological order. But if we fuse them, we just got 2 gap domain walls here. This is because like 2 of the invertible domain walls here is induced from the algebra non-trivial algebra automorphisms of A plus B. So here is an example beyond the group symmetry, which is the double Ising topological order. So there are three condensable algebras in a double Ising, which condense to vacuum or toric code or itself. And we see the same phenomenon happens here. So the EM exchange domain wall here in the toric code model does not really affect the gapped domain wall if we close them. So this is due to the EM exchange here is induced by the non-trivial algebra automorphism phi of A2. Yeah. But although A2 does not affect the gap domain walls in the double Ising topological order, it indeed has some impact in the two-step condensation. So the obvious inclusion that A2 to AL would determine a two-step condensation process in which this A2 corresponds to 1 and the other component sigma box sigma bar would correspond to both E or M. In the sense that if we compose this inclusion I with this non-trivial algebra automorphism, we would obtain a new two-step condensation I prime. Yeah. So AL has two incarnations, 1 plus M and 1 plus E in the toric code model under this condensation process. However, if we fuse them again, we just got one gap boundary of the double Ising. So this invertible domain wall does not affect neither the gap domain wall of the double Ising or the gap boundary of double Ising. And we have a similar situation for S3 topological order. For S3 condensed to the Z3 topological order. But in this case, the EM exchange domain wall is induced from comes from the CF exchange domain wall in the original S3 topological order. So it does impact the gap domain walls if we close them. However, we have another invertible domain wall here, which is induced from the algebra automorphism phi of A plus B here. So the 1-to exchange means that we exchange E with E squared and M with M squared. Okay, but in this time, the 1-to exchange domain wall does not generate new gap boundaries in the two-step condensation, because if we include A plus B to the Lagrangian algebras in S3 topological order, we got A plus B plus 2F and A plus B plus 2C. That is 1 plus M squared and 1 plus E squared. So the 1-to exchange domain wall preserves these Lagrangian algebras. Yeah, in the Z3 topological order. Yeah, I'm finished. Thanks.
Thank you. So is there any question or comment from Nagoya? So we have one question, so please wait a moment.
Thank you for the talk. So in the case of toric code, for example, if you consider EM exchange domain wall on a segment, finite segment, not just whole boundary, but in the bulk, but only finite segment, there's a paper showing that the endpoint of the domain wall behaves like Ising anyons. Can you say something about that kind of finite segment of domain walls in the bulk?
You mean the finite segment boundary of the bulk? Sorry, I haven't heard this terminology before.
I see. Yeah, in just usual spin, that is realization of toric code. People just introduce some modification of Hamiltonian such so that there's some finite region, finite 1D like region in which the which behaves like EM domain wall, but there are two endpoints, and the endpoints behaves like Ising anyons. So I wonder if this kind of categorical characterization is possible for those finite domain walls.
I'm not sure, but it sounds interesting, so I may check that
Uh-huh.
later.
Okay. Thank you.
Any other comment? Question? Online, is there any question or comment?
Yeah. So,
So please.
are you able to hear me?
Yeah.
Yeah. Hey, Ronga, it's Hank. So, thanks for the nice talk. I have a couple of kind of clarifying questions. So, here by two Morita equivalents between these A1 and A2, you're thinking about I want to understand the context, the Morita context. So, here you're thinking about like the local modules
Yeah.
over A1 and local modules over A2. They are
Yeah.
two Morita in the context of like a bigger two category, right?
Yeah.
So what is the bigger two category?
The bigger two category.
Yeah. So what do you mean by two Morita?
So our definition is actually like a incursive definition. So one Morita equivalent means that they're module category equivalent.
Mm-hmm.
Yeah. Yeah. So we define the two Morita equivalent as so their module categories are like one Morita equivalent.
Okay. Okay, I see. Okay. So like they have the same center. Is that true or?
They have the same center.
Yeah, like these two categories, they have the same center? Or like what do you mean by two categories being Morita equivalent? Like you have to phrase that in like two vector or something, right? Or
No, we didn't think about that. Actually, we didn't appeal to the two category.
okay. So my second question is how much of this is true in the case of, let's say, quantum Hall effect? Like I give you level one U1, you know, and then the category is no longer fusion. So, you know, how much of this is still true?
I'm not sure yet.
Okay. Yeah, just that the one last comment is that in the quantum Hall, you're able to thread a flux through the quantum Hall torus, but when you cut it in half, then well, the domain wall is no longer gapped. There's a compact boson on the circle. So yeah, I think this is only true for gap boundaries, but
Yeah, maybe. I don't know. We should discuss it maybe
okay,
later.
sounds good. Thank you.
Any other question? So then let's thank Shu-san again.
Yeah.
The next talk will start on the own schedule.
はい、テストです。これでいけますかね、多分。ここオフになってるんですよね。うん。なんかいけるかな。はい、はい、はい。これでどうですか？大丈夫ですね。はい、ありがとうございます。じゃあちょっと待ってください。画面共有。で、出て。これフルスクリーンになってないんでしたっけ？なってますよね。いけますね。はい。ここでは切れてるんですけどね、参加者で。こっち切れてないですね。参加者、僕の画面だと切れてるんです。はい。だから自分は見えないんです。なんかこれ、ボタンでませんでした。あ、これで最小化すればいいです。これで最小化したいんですか？これ、素晴らしい。ありがとうございます。
So let's start the next talk. The speaker is Hamanaka-san from Nagoya. And he will talk on the four-dimensional WCW models and the unification of integrable systems. So please start.
Thank you for the introduction. So first of all, I'd like to thank the organizer for giving me an opportunity to have a talk here. This talk is based on the collaboration with Sanchi Fan-san and Kanno Hiroaki-san here in Nagoya. And the paper is this one. This is a full paper. And recently, I submit the shorter proceeding papers last month. And this Monday, it's accepted. So the version 2 will appear soon, I hope. Probably this is very, very short. So I recommend firstly, you check this shorter version. And if you are interested in, please read our full paper. But yeah. Anyway, today I'd like to discuss this best-minute model in 4 dimensions. But this closely relate to フリーズした。どうしよう。slide is freeze. I'm sorry. So I'd like to try the screen. They appear very, very slow. It's okay. Okay, continue. So this model have the close relation to the anti-Selderian equation in 4 dimensions. So in the introduction, I'd like to introduce a motivation why I focus on this equation today. Okay. So the anti-Selderian equation is actually very, very important equations in physics and mathematics. And especially the instant solution, which is a special soliton-like solutions that play very important roles in quantum field theories and geometry and so on. This soliton is localized at a point in 4 dimensions in this diagram. So in this diagram, action density is localized at a point in 4 dimensions. So this is a codimension 4 solitons. And usually we discuss the behavior of the soliton by analyze the energy density, but this is a Euclidean. So instead of the energy density, we usually use this action density, trace F mu nu, F mu nu. This is just a second Chang class in mathematics. And this instanton actually reveals the non-perturbative aspects of quantum field theories. And furthermore, applied to the geometry, especially four-dimensional differential geometry, by constructing the Donaldson invariants and so on. And furthermore, this is also very important in integral systems. Actually, the self-Dirichlet equation is a kind of master equation among the integral systems, which is first conjectured by Richard Ward in 1985. He conjectured that many, or perhaps all, integral equations can be derived from the anti-Dirichlet equation by deduction. So this conjecture is very, very mysterious and fantastic, actually, because in lower dimension, there are many kind of integral equations, such as KdV equation and Sine-Gordon and Toda equation and so on. They look like all much different. But actually, all these equations can be derived from only one equation, anti-Dirichlet equation in 4 dimensions by deduction. This is surprised and summarized in the book of Mason and Woodhouse very beautifully. And furthermore, self-Dirichlet equations can be understood in the framework of twistor theory. And there is a solution generating technique. And this technique is also reduced to lower dimensions. So this is a kind of unified theory of integral systems, I hope. Okay, so anyway, firstly, I'd like to introduce the self-Dirichlet equation and the one example of Ward conjectures. Now, anti-Dirichlet equation is defined in 4-dimensional space-time. And this is defined as the anti-Dirichlet duality of the field strength F mu nu in the sense of Hodge dual. So this one. So now the suffix mu nu runs from 1 to 4. And this F mu nu is called the field strength. And defined as follows. And this A mu is a gauge field. And now Yang-Mills gauge group is assumed to be GLNC or subgroups. So then gauge fields and field strengths take values in n by n complex matrix. So this equation is a differential equation for the n by n, the gauge field, and can be written down in the component as follows in the real representations and complex representations. And today, I further rewrite the final form into the Yann's form. So this is called the Yann's equation. Actually, Yann's equation and self-Dirichlet equation are equivalent. So not difficult to prove this equivalence, but today I don't discuss the details. Okay, so now let me introduce one example of the Ward conjecture. So reduction to nonlinear Schrödinger equation from self-Dirichlet equations. So now the Yang-Mills gauge group is U2, SU2. So let's start with the self-Dirichlet equations with gauge group with SU2. So now F mu nu and so on are all 2 by 2, 2 by 2. And there are 2 steps to give a nonlinear Schrödinger equation. So the first step is that just a simple dimensional reductions in these directions. So now 4-dimensional equation is reduced to 2 dimensions. And in the second step, we take the following non-trivial reduction conditions for the gauge fields. So this is very, very non-trivial. And now psi is one the new variables. depend on the remaining two variables, z and x. X is a linear combination of w and w tilde. So then, the first equation and the second equation of Yamid equation is automatically solved. And the final equation gives the following relations with respect to the psi. And this is just a nonlinear Schrödinger equation. So this is very, very miracle. But in this way, we can get various kind of integrable equations in lower dimension from the four-dimensional self-real Yamid equation. But now I'd like to emphasize that we should take not the Euclidean signature, but the split signature, plus, plus, minus, minus, because there are time z derivative here. This can be identified with the time coordinate. But z is z comes from here, and in the Euclid signature, z must be complex, actually. But usually, nonlinear Schrödinger equation can be defined in real two-dimensional spacetime. So this is a contradiction. But in the split signature, z can be real, actually. So we usually take the split signature in the discussion of the word conjecture. So I would like to emphasize this point. And finally, I'd like to mention the unified theory of integral systems. So usually, self-real Yamid equations is discussed in the context of Yamid theory. But today, I'd like to discuss in another context. So recently, there are hot topics on the unified theory of integral systems based on the two kinds of master theories, the four-dimensional Chern-Simons and the four-dimensional Bess-Minelitten model. And the Bess-Minelitten model side, the equation of motion is just the self-real Yamid equation, actually. So the right side, we can apply the word conjecture, and this gives rise to the various integral equations, such as KdV equations, and so on. On the other hand, in the left side, the four-dimensional Chern-Simons theory actually gives rise to the various solvable models, such as spin chains and principal chiral models, and so on. And firstly, discussed by Costello, Yamazaki, and so on. And now many people study this one very intensively. But furthermore, this is unified in by the six-dimensional Chern-Simons theories. So this discussion is made by Wittels and Skinner very recently. They prove that this six-dimensional theory gives the four-dimensional Chern-Simons in one direction by deduction in some sense. But in another direction, this gives rise to four-dimensional Bess-Minelitten model. So this is a kind of a double fibrillation. So there should be a duality relation between four-dimensional Chern-Simons and four-dimensional Bess-Minelitten model. And many people believe that this might be a unified theory of integral systems, which includes both spin chains and KdV and so on. And furthermore, there are non-trivial duality relations, I hope. And I would like to emphasize that we should take the split signature. Okay, so this is the introduction, and I'd like to discuss the soliton solutions of self-real Yamid equation in this context. Okay, this is the introduction, and just 12 minutes. Yeah. So I hope 37 minutes. No problem. Too long. Okay. Okay. So but please note that my discussion is all simple. So in the next section, I'd like to introduce the model, and in the section 3, I'd like to construct the soliton solutions and discuss the behavior. And the final section, I'd like to discuss the future direction. This is also the important point in this talk. So discussion is very easy. The model is this one, and the solution is this one, and the behavior is this one. So very, very simple. And I note that I'm not a mathematician, and I'm not a physicist. So please be easy. There's no rigorous proof. But actually, yeah, actually discussion is actually rigorous. But today's talk is essence only. So detail is not important. Okay, so in this section, I'd like to introduce the four-dimensional best-fitted models. So this model is a analog of the two-dimensional best-fitted model. So this two-dimensional best-fitted is very, very famous conformal field theories. And there are many, many studies. But the four-dimensional version is not so famous. And firstly discovered by the Donaldson, actually. And in 1960, Joseph Moore, Nicholas of Shattersbury, and Inami-san, Kanno-san, Ueno-san, Shion-san discussed the conformal field theory aspects of this model. But after that, there are very few studies so far. But I think this is very, very important and very interesting. Because this have the conformal field theory aspects, but the equation motion is Young's equation, actually. Young's equation is equivalent to the self-Rayleigh equation. So this possesses the integrability aspect in this sense. And furthermore, in the split signature, plus, plus, minus, minus, the best-fitted model is just the same as the string field theory action of n equal to string theory. So there's a connection to the string theory in this signature. So this point is also very, very important. So today we focus on the split signature by this reason. Okay, and so now we construct the Soliton solutions of this model. So this directly can be applied to this n equal to string theory and so on, I hope. Okay, so let me show the action. So this is a starting point of this model. The best-fitted model consists of the two parts, sigma model action and best-fitted action. The sigma model action is defined as follows, and the best-fitted action is defined as follows. And now dynamical variable is sigma. And sigma take values in some group G. And I note that this G is not different with Yamil's gauge group. And now G is GLN, or the subgroup. And in fact, this looks like the two-dimensional best-fitted model. But the difference is here. So there is a Kähler 2 form omega here. So totally four forms. So defined on 4 dimensions. And now we discuss the flat space only. So omega is explicitly given by this one. And the local coordinates ZW, Z tilde, W tilde, and so on. But details is not important. There actually exists the model. And the equation motion is easily derived from this action. And this is just the Young's equation. And which equivalent to the self-Rayleigh equation. So now we solve these equations. Okay, so now I'd like to mention the relation to the n equal to string theory. So I remember this morning, the Shanahan-san discussed the n equal to 0 string theory, the bosonic string theory, and perhaps briefly mentioned the n equal to 1 string theories. So this n just corresponds to the number of worldsheet supersymmetry. So n equal to 0 string is just a bosonic string. whose target space is 60, 20, 26 dimension, 26 dimension. And the field content is this one. So the gravity and the B field, the dilaton, and so on. The many field contents. And n equals 1 string is a standard superstring theory, whose target space is 10 dimensions. And the field contents is also many, G mu nu, B mu nu, and so on. And n equals 2 string is just the n equals 2 string. And whose target space is 4 dimension actually. And exactly speaking, 2 plus 2 dimension. So the signature is plus minus actually. And the important point is this one, the field contents is massless scalar only actually. So this is very surprising. And n equals to string theory, string field theory is would be expected to be very simple in terms of the massless scalar phi only. And in 1991, Ogri and Buffer proposed the string field theory actions of this n equals to string theory. And the relationship between the best unit model is this one. The sigma is exponential phi, actually. Phi is a massless scalar field in the n equals to string theory. So now we define the four-dimensional best unit model as action. And we can substitute this relation into this one. Then this action can be related in terms of the phi. And this is actually the n equals to string field theory actions. And then we can analyze various physical quantities such as endpoint functions and so on. And Ogri Buffer proved that this coincides with the worldsheet calculation and so on. But this is a guesswork, actually. He just proposed as one candidate. Actually, I'd like to remark that the Chan, the speaker this morning, I'm sorry, this next, not the next speaker. I'm sorry, program is changed. So yeah, he is my PhD student in Nagoya. And he studied the homotopy algebra formulation of this n equals to string field theory, actually. And finally, I would like to comment again. Yeah, okay. Okay, so the next section, I'd like to construct the Soiton solution of this self-derivative equation, the Yan's equations. And the Yan's equation is defined right here. And now we focus on the split signature, so ultra hyperbolic spaces. So the Z tilde and Z and so on is defined as follows. So now all Z, W, and so on are all real, actually. And this give rise to the ultra hyperbolic spaces because the original metric is this one. But if you like the split signature, if you prefer the Euclidean signature, then it's okay. Yeah, then you can take another real slice like this right side. Then this setting gives rise to the Euclidean space. So no problem. Yeah, anyway, so let's solve this equation. So in order to solve this one, we take the Lux representation as in the integral systems. So this is given by this one. And there's a spectral parameter, zeta. But I'd like to note that this zeta is now n by n constant matrix. So not a scalar matrix. This point is important so that the solution becomes non-trivial. Yeah, anyway, compatible condition give rise to the Yan's equation. Okay, so let's construct the non-trivial solutions. So firstly, I'd like to define the double transformation, which leave this linear system as it is. So in order to define the double transformation, we have to prepare a special solution for a special value zeta. So special value of zeta is denoted by capital lambda now. And the corresponding special solution is psi. Theta, I'm sorry. Theta is a special function of f. Then a double transformation is defined in this way. And we can prove that under this double transformation, the linear system is a form invariant. So we can generate the new solution from known solution by using this double transformation. So the starting with the trivial solutions, and by n iterations of this double transformation, we can get the following non-trivial solutions. So this is Wronskian type solutions. Actually, our Soiton solutions have the very similar behavior of KP solitons. And the exact solution of KP equation is described by Wronskian, actually. And this is the first example, would be first example of the Wronskian type solution of self-derivative equation, we hope. And this, all ingredient is now n by n. And this theta satisfies the following dispersion relations. But in fact, this is not the determinant, but the quasi-determinant actually. There's a box here, So this is a quasi-determinant actually. And the quasi-determinant is one of the non-commutative version of the determinant. And there are several definitions, but now we take the following definition, which is the most simplest definition as a sure complement. So this is well defined. So now small d is n by n, and totally n by n. And this can be applied to this solution because each element is n by n. And the definition is this one. So d minus c a inverse b. So this solution sigma n is 0 minus this part minus this square part inverse times this column parts. So well defined and totally n by n. And Soiton solution is also obtained. The Soiton solution have the exponential linear function. So now we focus on the SL2C case. And so all ingredients is 2 by 2. And theta is 2 by 2, and there is an exponential linear function of space-time coordinate as follows. I'm sorry, this is detail. Detail is not important, but this is the exact solution, and give rise to the Soiton solution actually. And the group can be unitary actually. Anyway, this is a solution. So now let's calculate the action density. Action density is essentially energy density. So we can discuss the behavior of the Soiton solutions. Okay, so this is the one Soiton solution. This is very, very simple. And the action density consists of 2 parts. And the sigma model action is this one. So there's a check square function. The check function is this one. Check function is a 1 over cos x. And there's a square. Actually, this is a typical one Soiton solution. And sorry, this large x is a L plus L bar. And L is a linear function of x. So totally real valued linear function of x. And the peak lies on the large x equals 0. So which defines the 3-dimensional hypersurface. So this configuration is localized on the 3-dimensional hyperplane. So absolutely not instantons, but the codimension one hyperplane solitons in 4 dimensions. And the best minimum term is identically 0. So this is a totally action density or energy density. So this is very, very similar to KP solitons. The KP case, the solution is also check square of x. Large x is a linear function of t, x, and y. So the peak is peak lies on the 2-dimensional plane in 3 dimensions. So our solution is a 1-dimensional extension, higher extension of this KP soliton. Okay, so 2 solitons, the result is this one. The sigma model action is explicitly calculated in very compact forms. So this is actually non-singular. And in the asymptotic region, almost 0. But in some 2 directions, this is non-zero and look like the 1 soliton. So this suggests that two intersecting 1 soliton. But actually, the position is shifted. This shift is typical in soliton theory and called the phase shift. This due to the nonlinear effects. So anyway, roughly just intersecting one solitons. Okay, so how about the best minimum terms? Unfortunately, there are many long terms in this calculation. This is actually non-singular, but never non-compact, never compact. But at least in the asymptotic region, this is 0 in any directions. So the contribution arises only in the middle region. So total action density is a sigma model action, the intersecting 2 plane, intersecting one solitons plus dodging effect in the middle region. So like this one. Okay, so in this way, we can analyze n soliton solutions. So we take only the asymptotic behavior. And the result is that this is a nonlinear superposition of n1 solitons. So like the KP solitons. Okay, so finally, I'd like to make some remarks. So first one is a reduction to 1 plus 2 dimensions. So now we discuss a 2 plus 2 dimensions. So this is a 2-time physics. So what's a 2-time physics? That's crazy. Yeah, it's okay. So let's reduce to the 1 plus dimension. It's possible by taking a translational invariance. Then time coordinate becomes 1. So standard, the 1 plus 2 dimension world. So the soliton solution is easily constructed. Then we can define the Hamiltonian or energy density from this Lagrangian. The result is that the best minimum Hamiltonian identically vanish. So the contribution is from nonlinear sigma model term only. So the 1 soliton solution is this one, codimension 1 solitons, and 2 solitons is perfectly intersecting 1 solitons. So in this 1 plus 2 dimensions, the behavior is very, very close to KP solitons without the contribution of the middle regions. And the hyperplane is perfectly the same between the energy density and action density. So it might be reasonable to discuss the action density in 4 dimensions. Okay, so another one is the instanton case, but I have a little time, so I like to skip this one. Okay, so I'd like to conclude today's talk. So we constructed the new type of codimension 1 solitons, which are not instantons, and calculate the action density of this model. And the behavior shows that there exists the intersecting codimension 1 brains, and in the context of n equals to strings theory. So this would be a new physical object. So there would be a various application to this string theory. And there are many future works to be seen. But I pick up the three of them. The first one is the classification of this soliton solutions. And the second one is quantization. And the final one is a non-computative space extension. The first one is this one. Okay, so let's focus on this intersecting two solitons. And I mentioned that there is a position shift, the phase shift here. So this suggests that there is a dissonance actually. So this is line, but now this is a hyperplane. This phase shift can be right side or left side. And if this delta is right side, there must be a dissonance state of this one. Then this delta is right side. And if delta is left side, the dissonance, this configuration would be the dissonance solution of this one. So T channel. The left side is the S channel, and this is a T channel. So this is actually the origin of the phase shift. Usually discussed in KP solitons and so on. And for the KP solitons, so that's why the Y-shape soliton interaction is a building block. And there are many kind of soliton waves by combining the Y-shape soliton interaction. And these are perfectly classified in terms of the positive Grassmannian and developed by Kodama-san and Williams-san. So this is actually very beautiful theory and summarized in the book by Kodama-san. So I strongly recommend this one. So we can expect this would be possible for the four-dimensional self-Riemann equations. And actually, the resonance solution is work in progress with the Sanchi Fan-san in Nagoya and Shanshai Li-san and Dajun Chan-san in Shanghai University just now. So we expect the soliton plane wave would be classified in terms of some geometrical objects. And we can clarify the moduli space of these solitons and can be applied to the quantum field theory of n equals to string theory, and perhaps the geometry as a new invariants. Okay, so this is the first one. And the second one is the quantization. So let's return back to the unified theory of integral systems. So I mentioned that the four-dimensional best-united model is a string field theory action of n equals to string theory. So we can quantize this action in standard way. And we can calculate the endpoint functions. And so our goal is vanishing the higher point functions. And now Shanghai Chan-san want study this problem via the homotopy algebra formulations. Actually, this is very powerful because recently Yuji Okawa-san gives some formula of correlation functions in this homotopy algebra formulations. And so if Lagrangian is given, the correlation function is automatically produced by picking some data of homotopy algebra. So we expect by using the homotopy algebra formulation and Okawa's formula, we can prove the vanishing higher point functions, because endpoint function is also calculated by Okawa's formula. So we can, so I'd like to propose the other future direction, homotopy algebra formulation of the Lagrangian formalism of integral systems. especially Lagrangian multiform theory of integral systems. This is developed by Frank Nijhoff and Ulyss Lys and their colleagues. And so this theory is one of the Lagrange formalism of integral system, but in which the infinite symmetry is manifest actually. So the quantization, so there should be a systematic quantization for this theory via the homotopy algebra formulation, because by using the Occam's formula, this Lagrangian gives rise to the scattering amplitude, and the total set of scattering amplitude is the S matrix. And S matrix factorization is one of the quantum integrability. And this just gives rise to the Yang-Baxter equation. So I hope the homotopy algebra formulation would be the bridge between the quantum integrability of Yang-Baxter equation and classical integrability of the infinite symmetry. So this would be a very interesting future direction, I hope. And of course, if so, the infinite symmetry is broken in the quantum process, there should be an anomaly. And this can be called the integrability anomaly. So this is also new. So, and I hope this is also interesting. And finally, I'd like to skip the non-commutative space extensions. I hope this is also interesting, but I'd like to skip. Okay, thank you very much.
Thank you very much. So is there any question or comment from Nagoya?
Oh.
No? How about from Zoom online?
Yeah, can I maybe ask a pretty basic question? So I'm interested in the 2+1D theory that you talked about.
Where? 1 plus 2 dimension, perhaps?
Yeah. So is that theory?
This one. This one.
Yes. So is that theory topological holomorphic, like from this reduction that you get?
Oh, sorry. Sorry, I missed your question. What's your question?
Yeah. So is this theory topological holomorphic?
This is topological holomorphic. Not totally not topological. And holomorphic in this sense, yeah. Original in 4 dimension, this is holomorphic. And in some sense, yes.
Like, I guess it's possible to put this theory onto like R times C or R times CD1 or something like that.
Probably, yeah, it's possible, I think, yeah. Now I focus on the flat space only, but yeah.
Okay.
Yeah.
Thank you.
Thank you.
Any other question? No? Then let's thank Hamanaka-san again. The next speaker, Zhang-san, Zihao Zhang-san. Can you hear me? No.
Hello? Maybe he misunderstood the time. So, uh, hmm. Maybe he misunderstood the starting time. So I use Japanese time. Sorry. So in that Excel file, I use Japanese time. Clearly, I write down JST, but many people misunderstand. This one was the Chinese time. Uh, uh. いるやん。ハロー、困るんだけど。 Hmm.
Maybe this time, but the speaker doesn't appear, so
Mm. Hmm? G? Eh? G、ハオシュウ、ハオシュウ。あ、そうか、いいのか。So, hello, where's the house shoe? Final speaker.
I'm online.
You already prepare. Okay. But the another speaker, Ji Hao Jian, Ji Hao Zhang, he is not yet.
Uh-huh.
Oh. How can we contact to him?
I think his account is online currently, but he's not responding. Maybe he's not at his computer right now. I'm not sure.
Because maybe he completely misunderstood the study time.
Yeah, so I've already messaged to Zihao on WeChat. So, oh yeah, he didn't respond.
Oh, he didn't respond.
Yeah, I'm really sorry about this.
Maybe. Why he? Very serious. あれ、何してんねん、私。So maybe it is better to make some video call to him. So then he should.
I don't have his number. Sorry. I only have him on WeChat. So, oh yeah, I wonder where he is.
Hmm. なんだ、これはもう。あれ、ああ。ああ。ここか。
Zhang-san, can you hear me?
Yes.
So yeah.
Okay,
it's
sorry.
Yes.
But I think the schedule is maybe 20 minutes later.
So please share
Okay.
the screen.
Yes. Okay, so let me share the screen. Okay. See my screen?
Yeah, it's okay.
Okay.
I can see you.
Okay. Then
Please full screen nice.
yes.
Yeah, it's okay. So, are you ready?
Yes.
じゃあそう。じゃあ next speaker is ジハオザンさん、from Beijing, and he will talk about the two character theory of finite two groups. So please start.
Okay. So first I would like to thank the organizers for inviting me to give this talk. Today I'm going to talk about the two character theory of finite two groups. Okay, and this is based on joint works with Mo Huang and Hao Xu. Okay. And first, I would like to review some basic results about the finite group representation theory. Okay, and the first result, we know that the category of finite dimensional representations of finite group G is finite semi-simple. And we always work over the complex number field. Okay, and equivalently, this is the group algebra KG is semi-simple. And for representation V, we can define its character by taking the trace of the rho G, the operator rho G, okay? So, and we know that character, this function is conjugation invariant, which means kv of H is equal to kv of GHT inverse for all elements G and H. Okay, so this means the characters are class functions, which are functions constant on every conjugate class. And we can also define an inner product on the space of class functions, and the characters are mutually orthogonal on the under this inner product. Okay, so more precisely, you have an inner product of kv and kw is equal to the dimension of the Hom space of v and w. Okay, and if v and w are irreducible representations, we know the inner products are 1 or 0, depending on whether they are isomorphic or not. Okay, and we're going to generalize these results in the two representation theory of finite two groups. So the first question is, what is a two group? Okay, and indeed there are many different models for two group, and here we take the model of weak two groups. Okay, so in this talk, a two group is just a monoidal category, and in which every morphism is invertible, and every object is also invertible. Okay, but for the objects, they are invertible up to isomorphism. Okay. And given the two group, we can define the notion of homotopy groups. The first homotopy group Pi1 is defined to be the group of isomorphism class of objects in G, and the group multiplication is given by the tensor product of these two groups. Okay, and for the second homotopy group, it is defined to be the automorphism group of the tensor unit. Okay, and if both of two homotopy groups are finite, we see this two group is finite. And in physics, the homotopy groups, this Pi1 is called the zero form symmetry group, and the Pi2 is called the one form symmetry group. And to determine the two group, we also need a spherical homology class, which is known as a Postnikov class or the K invariant. Okay, and the spherical cycle representing this homology class is given by the associator of G. Okay, the associator satisfies the Pentagon equation, and in these two groups, the Pentagon equation is just the co-cycle equation of this alpha. Okay, and the action of pi1 on the pi2 is given by the conjugation. Okay, and we can define the notion of finite semi-simple two representations. It is just a finite semi-simple category and equivalent with a two-group action. And all the finite semi-simple two representations form a two category. We denote it by two rep. Okay, and we can also define the two-group two algebra. Okay, what is the two-group two algebra? It can be defined in two steps. The first step is to linearize the Hom space. Okay, so from the two-group G, we linearize all the Hom spaces. So we get a K-linear category. We denote it by K star G. And the second step is to take the Karopi completion. Okay, the result is given is denoted by vec G. Okay, this is what we define the two-group two algebra. Okay, and by the universal property of Karopi completion, we know that the two representations of G are equivalent to the modules over vec G. Okay, because you can view the vec G as a linearization of G. Okay, but we also need Karopi completion to make vec G have a better property. Okay, so vec G just categorized as a group algebra or finite group. And when G is finite two group, this vec G is a so-called multifusion category. Okay, it is a finite semi-simple rigid monoidal K-linear category. Okay, rigid just means every object has left and right dual. And for two group G, the dual of an object is just given by the inverse. Okay, and multifusion category is the categorification of semi-simple algebra. Okay, so by a theorem of Douglas and Reuter, the two rep G, this two category, is a finite semi-simple two category. Okay, and the notion of finite semi-simple two category is also defined by defined in Douglas and Reuter's work. Okay. Okay. Moreover, if we have two finite semi-simple two representations of V and W, we can take the linear tensor product, and there is a diagonal G action. Okay, this like the tensor product to representations of a group. Okay, so we obtain the tensor product on the two category two rep G. Okay, this is symmetric monoidal structure. Okay, and also given the two representation V, it has a left and right dual in this symmetric monoidal two category, and the dual is given by the opposite category V op, just by inverting all morphisms. Okay, and there are evaluation morphisms from V op tensor V to vec. This is given by the Hom functor. And we also have the co-evaluation one morphism from vec to V tensor V op, which maps the one-dimensional vector space K to this direct sum. Okay, so this tells us that two rep G is a symmetric fusion two category, yeah, in the sense of Douglas and Reuter. Okay, now we are going to define the notion for two character. So we recall for group G, the character per representation is defined by taking the trace. So to define the two character, we need to categorify the notion of trace. Okay, so first, the trace. Okay, so the above trace to define the character. This trace is the trace in the category of vector space in vec. Okay, and this notion can be easily generalized in any rigid symmetric monoidal category. Okay, and this is well known. We can use this graph calculus to define the trace. We start from the one-dimensional vector space K, taking the co-evaluation morphism and taking the G action, and finally we take the evaluation morphism, and this is just a trace of rho G. Okay, and now we work in the two category of two vec. It is a two category of finite semi-simple categories. Okay, so it is also rigid. Okay, so we can also define the notion of trace in this rigid symmetric monoidal two category. I just use the same graph calculus. Okay, so for finite two group G and the two representation V, we define the two-character KV as follows. A KVG is a composition of three one-morphisms. Here, one-morphism are just functors. Okay, so first we take the co-evaluation morphism, and we take the G-action functor and the evaluation morphism. Okay. So KV of G is a functor from VAC to VAC. And we know the end of functor category of VAC is just VAC itself. So we can identify KV of G with a vector space. Okay, so we can view KV as a functor from the two group G to VAC. And we can also compute this composition of three functors because we know the explicit expression of co-evaluation and evaluation morphisms. And we see KV of G is isomorphic to the space of natural transformations from the identity functor to the G-action functor. Okay, and this coincides with the categorical trees defined by Gantner and Kapranov. Okay, they define the notion of categorical trees in any two category without the monoidal structure or the rigidity. So here we use the rigid symmetric monoidal structure of two VAC to define the categorical trees, and they are the same in this special example. And also the two-character KV defined as above has conjugation invariance. So for two objects T and X, we have a canonical isomorphism of vector space from KV of X to KV of GXT inverse. Okay, so here we omit the brackets, so GXT inverse. We can use the coherence theorem just so this is an object. Okay, and this isomorphism is given by compose with a natural transformation with the G action functor and the G inverse action functor. Okay, and moreover, these isomorphisms satisfy some higher coherence relation. For example, we have this commutative diagram. Okay, and what does this mean? This means KV has a structure of a homotopy G fixed point. Okay, so so let me explain. For a fixed point, it means KV of X should be equal to KV of GXT inverse. Okay, but now they are not equal. They only isomorphic and naturally isomorphic up to some higher coherence relation. Okay, so this is what we mean by a homotopy fixed point. Okay, here G action is given by the conjugation. Okay, so KV can be viewed as an object in the equivariantization category, equivariantization of this functor category. Okay, here the equivariantization is the same as the homotopy fixed point. Okay, and such a functor we call it just a class functor because it categorifies the notion of class functions. Okay. And we also have an equivalence from VAC-G to this functor category. And the first equivalence from VAC-G to VAC-G-op is induced by the equivalence from G to G-op, which acts as identity on objects and send each morphism to its inverse. Okay, and the second equivalence, this is the Yoneda embedding. And the last one, this is given by the universal probability of Carby completion. Okay, and this equivalence categorifies the Fourier transform for finite abelian groups. In the next talk, in the next Haoxu's talk, he will discuss this topic. Okay, and also we can see that phi is an equivalence of G modules. Okay, so this means it preserves the G action. Okay, G action on both sides are given by the conjugation. So we can take in the equivariantization and we still obtain an equivalence. And moreover, we have, by definition, we can check the Drinfeld center of VAC-G is the same as the equivariantization of VAC-G. Okay, so we get equivalence from the trim field center of Vec to the equivocalization of this functor category. Okay. And under this equivalence, a two-character KV, okay, which is an object in the right-hand side, okay, we can view it as an object in the left-hand side. And here's remarks that since we have an equivalence from Vec to the functor category, we can transfer the monoidal structure on Vec. Okay, the Vec has a monoidal structure induced from that of G. Okay, so we can transfer this monoidal structure to this functor category. Then the monoidal structure on this functor category is given by the deconvolution, okay, defined by this coend. And also we can transfer the monoidal structure and the braiding, okay, the trim field center is a braiding monoidal structure. We can transfer this braiding monoidal structure to the right-hand side. This equivocalization category is also a braiding monoidal structure. Okay, and the monoidal structure is also given by the deconvolution. Okay, and now this is the main result of our work for a finite two-group G and irreducible two-representation V. There is a canonical isomorphism from phi of ZV to the two-character chi of V of. Okay, let me explain. Here is ZV. What is ZV? ZV is the so-called full center of V. And phi is defined in the previous page. Okay, just this phi. Okay, the full center is an object in this trim field center, and this phi maps it to this equivocalization category, and it's isomorphic to the two-character category of V of. And this full center is not only an object, it is also a so-called Lagrangian algebra. Okay, so what is the Lagrangian algebra? It is a commutative, connected, separable algebra, and it is also maximal in the sense that the category of local modules is trivial. Trivial means equivalent to Vec. Okay, so the full center is the Lagrangian algebra. Then this isomorphism shows that the two character is also a Lagrangian algebra. Okay, so the main result is that the two-character, irreducible two-character, okay, it has a structure of Lagrangian algebra in this equivocalization category. Okay, this structure is inherited from the full center. And we also know that the isomorphism classes of Lagrangian algebras in this trim field center are one-to-one corresponding to the equivalence classes of indecomposable Vec modules. Okay, and indecomposable Vec modules are just irreducible two representations. So this tells us that two representations are completely determined by their two characters. Okay. And here we also give a topological quantum field theory point of view. For a finite semi-sub two representation, it is a fully dualizable object in 2Vec. So by the cobordism hypothesis, we know that there's a two-dimensional fully extended TQFT, okay, valued in 2Vec, which maps a single point to V. Okay, but here V is also equipped with a G action, so this means this TQFT, its domain is not the usual cobordism category. It is a cobordism category equivalent with a G action. So which means the cobordisms, the zero-dimensional, one-dimensional, or two-dimensional manifolds, they are equipped with a map to the classifying space of BG. Okay, so you can see these manifolds, they are labeled by some defects. Their defects are labeled by the objects and the morphisms of G. And this label just depicts the G structure on these manifolds. You can view them, just label a morphism to the classified space. Okay, and given this two-dimensional TQFT, it is a functor. So it maps some objects and morphisms in the left-hand side, okay, maps these cobordisms to some linear objects. Okay, so for example, for this circle, this is S1, and here labeled by G means there is a non-trivial G structure on this S1. And as we know in the graph calculus, it maps this circle to the two-character KV of G. And for this cylinder, this is a two-morphism in the cobordism category, okay, because it's two-dimensional. This is a two-morphism from the bottom circle to the top circle. So after we map it to 2-vec, it is a morphism from KV of X to KV of GXT inverse. Okay, so this is just a conjugation invariance morphism. Okay, and for these pans is the multiplication of the character. Okay, as we show the two character is an algebra. So what is the multiplication of this algebra? Okay, this pans just gives the multiplication. Okay, and we can also study the parting function on torus. These two circles that depicts the G structure on this torus, and there is an obvious modular group representation on this joint two character. This is what we call for this parting function. Okay, and I think I have no time, so I just briefly reintroduce the last result. We can also define inner product on the space of class functors. Okay, but the inner product is just a vector space. Okay, it is also the value of the convolution product at the unit, but there's also a pi1 G action, and we need to take the G covariance structure. Okay, so we just get an inner product, and we can show that the inner product of two characters is isomorphic to the dimension of their Helm spaces. Okay, but here the dimension is also vector space. Okay, so this result is the same as the orthogonality result for one group. Okay, so in this two group case, we also have this orthogonality result. Okay, so that's all. Thank you.
Thank you very much. So, is there any short question or comment? From Zoom, is there any short question? Then let's thank Zhang-san again. And the final speaker, Hao Shu-san, are you ready?
Yes.
So please share the screen.
Can you see my screen now?
Not yet. Yeah, it's okay. Can you see
it says some weird security check you need to bypass. I don't know. Yeah. If I change the slide, can you see it changing?
Yeah, it's okay. Yeah.
Okay.
So then let's start the final talk of today. So the speaker is Hao Shu-san from Göttingen, and the title is Pontryagin duality for two groups. So please start.
Yes, thanks for, first I want to extend my sincere gratitude to the organizers for organizing and of course inviting me to speak at this workshop. It is an honor to have the opportunity to present my recent research jointly with Mo Huang and Zhihao Zhang. However, before diving into my presentation, I feel it is important to take a moment to address a tragic and deeply shocking event that occurred on Wednesday. As many of you may have already known, a 10-year-old Japanese schoolboy was brutally attacked with a knife in Shenzhen, China, and tragically lost his life. Words cannot fully convey the heartbreaking and devastation that his family and loved ones must be enduring. This senseless act of violence is something none of us can truly comprehend, and I want to take this moment to firmly condemn such acts of terror. My heart goes out to his parents, and I offer my deepest condolences for their unimaginable loss. It is my hope that through greater communication, understanding, and compassion between communities, we can prevent such tragedies from happening again in the future. Now, with that said, let me transit to the focus of talk today. So my talk is about contrarian duality for two groups. So contrarian duality is an important notion to study representation theory of groups. So traditionally, for any abelian group A, one can define its contrarian dual as the group homomorphisms from A to U1. So as examples, we see that contrarian dual of Z is U1, and the dual of U1 is Z. And also we have that for any positive integer n, the contrarian dual of the cyclic group of order n is itself. However, there is no canonical choice of such an isomorphism. And for any two abelian groups A and B, their contrarian dual commutes with taking product. And if A is finite, its contrarian dual actually factors through a rational subgroup. So there's Q mod Z inside U1. Therefore, contrarian duality for finite abelian groups is determined by counting isomorphisms of such kind. So, or equivalently, we are actually counting non-degenerate pairings. So they are pairings of these finite field. So in an ongoing joint project with Mo Huang and Zhihao Zhang, we would like to categorize this above notion of contrarian duality. So let us first recall some basic notions. I think it's also introduced in previous talk, but let's just quickly remind. So for us, a two group is a monoidal category whose morphisms are all invertible, and objects are also invertible with respect to the monoidal product. We denote the group of isomorphism classes of objects by pi1, and the group of endomorphisms on monoidal unit by pi2. This notion is consistent with the topological approach, where one can deloop monoidal category to get a two category with one single object, and then this two categories geometric realization is a pointed topological space with pi1 and pi2 agree with our above conventions. A two group is finite if we have both pi1 and pi2 to be finite groups. A braided two group is a two group whose underlying monoidal category is now equipped with a compatible braiding. A symmetric two group is a braided two group whose underlying braiding is symmetric. So symmetric two groups are categorifications of abelian groups. And we are going to define their contrarian duals as follows. So let curly A to be a symmetric two group. We defined contrarian dual to be the category of braided functors from this curly A into BU1. So BU1 is a two group. It itself is delooping of U1, but since U1 is abelian, its delooping is again a two group. Okay, so this category of braided functors is equipped with a pointwise symmetric monoidal structure, which is inherited from BU1. And as examples, we have the follows. So if we take contradiction duals of BU1, we get back Z, and if we take dual of Z, we get BU1. Now, if we take contradiction dual of U1 viewed as a two group, so it's like sitting on pi 1, then its dual is BZ and turns out to be U1 again. For a finite cyclic group, if we take Z mod n and take its dual, we get BZ or mod over n. So there's like a 1 degree shift. And if we take dual, and then we get back. So also by definition, we can check that for symmetric two groups, the punctuation dual commutes with taking product. For finite symmetric two group, its punctuation dual also factors through this BQ mod Z. Now let's recall there is a stratification theorem saying that every symmetric two group is equivalent to one with trivial associators and uniters. In particular, such a strict symmetric two group is determined by abelian group pi 1, pi 2, and a group homomorphisms from pi 1 to pi 2. Unlike finite abelian groups, not every symmetric two group is punctuation self-dual. So using this above stratification theorem, we know that if a finite symmetric two group is equivalent to its punctuation dual, then we must have first pi 1 has to be equivalent to dual of pi 2, and pi 2 have to be dual of pi 1. And for a fixed choice of above equivalence, we need this group homomorphism F to be coincide with dual. Okay. And this condition is not to avoid. It's actually a very strong constraint of what kind of finite symmetric two group it should have. So let us recall the Fourier transform. So Fourier transform on a finite abelian group A can be viewed on different levels of abstraction. So the most naive understanding on the level of objects is the following. So for any C-valued function on A, we can define its Fourier transform to be a C-valued function on its punctuation dual as follows. And conversely, the inverse Fourier transform is just defined in the same way, but notice that we need to have this extra factor that divide by order of the group G. Okay. More importantly, Fourier transform and its inverse, they are not just isomorphisms of vector spaces, but also they are isomorphisms of Hopf algebras. So if we take the left-hand side to be regular functions on A, then the right-hand side would be the group algebra for A dual, etc. So it exchange pointwise product with convolution products. Then we can view it on the level of vector space. So for any finite dimensional A representations, there is a canonical A dual grading. And this A dual grading is given by so-called isotypical decomposition. So we can decompose V into direct sums of VP, where this VP is defined like this. So the action of X on V is in this component is given by P of X as a scalar times V. So this induces an equivalence of symmetric monoidal categories, actually. So the left-hand side, we have category of representations, finite dimensional representations of A. And on the right-hand side, we have category of A dual graded finite dimensional vector space. And notice that actually the above equivalence is a special case. So if we consider function A as an object in rep A, then what we get on the right-hand side is just the group algebra of A dual. Okay. And finally, you can even go higher to the level of categories. And then we will have an equivalence of symmetric monoidal two categories between the 2 rep A and 2 rep A dual. So they are like two representations of A and 2 representations of A dual. So we will have the following fact. So first, the category of finite dimensional vector space turns out to be an invertible bimodule between vec A and rep A. And rep A turns out as we previously said, by isotypical decomposition is equivalent to VEC of A dual. So VEC is the invertible bimodule between VEC A and VEC A dual. So, and given this finite semi-simple category C with A action, we construct its equivariantization. This is how we get from 2-rep A to 2-rep A dual. And conversely, if I have a finite dimensional, like finite semi-simple category D with an A dual action, then we can take the equivariantization and get back to a category with A action. Okay. Finally, we would like to categorify the theory of Fourier transform. So all those said, we have like different levels of abstractions to view Fourier transform on a finite abelian group. And now we would like to do the same for finite, not abelian group, but finite symmetric two group. So on the level of objects, what we have is the following, that whenever I have a functor going from curly A to VEC, then we define its Fourier transform using this co-end construction. So actually we should put things here, but since A is a finite symmetric two group, it's turned out to be the same. Conversely, the inverse Fourier transform is also now defined in a similar form for any functor from a curly A dual to VEC. And this provides us equivalence of categories between functors from A to VEC and functors from A dual to VEC. Okay. So Fourier transform described above gives an equivalence of symmetric monoidal categories. And the left-hand side, if the left-hand side is equipped with pointwise product, then the right-hand side is equipped with convolution product. And conversely, if the left-hand side is equipped with convolution product, the right-hand side is equipped with pointwise product. Moreover, depending on symmetric monoidal structures, there are several symmetric comonoidal structures such that altogether they form kind of Hopf algebra object in 2-VEC. Then these above equivalences preserve all these Hopf structures. Then going up on the level of one categories, what do we have? For any finite semi-simple category, actually, I think we should have a two category. Yeah, we should never. Yeah. So given such a representation of A, we can consider its isotypical decomposition. And this isotypical decomposition is given by component such that, so in here, this component VP consists of pairs. So a pair consists of an object in curly V, and then we need an isomorphism from like actions of X on V to this PX and tensor with V. So in some sense, this is like a categorified eigenspace for PX in PX. Yeah, but yeah, this is a natural isomorphism with respect to X. So we can vary X, and this will give me an isomorphism. And of course, these pairs satisfy some compatibility conditions I didn't specify here. So viewed as, sorry, this should be curly A hat grading on curly V. This provides us with an equivalence of two categories. So we have equivalence between 2-rep of A and 2-VEC of A dual. Moreover, this equivalence preserves symmetric monoidal structure. So if the left-hand side is equipped with pointwise product, then the right-hand side is equipped with convolution product. Here, I want to remind the audience that unlike abelian groups, the same underlying two group could have several different symmetric monoidal structures. Therefore, the equivalence seems paradoxical at first, because the left-hand side doesn't depend on symmetric monoidal structures, but the right-hand side obviously depends on symmetric monoidal structures. The reason is that even though curly A could have several different symmetric monoidal structures, which lead to potentially different entourage duals, they have to become equivalent after linearization. Interpreted in another way, this warns us that to determine the Pontryagin dual of curly A, it is not enough to know all the invertible objects, which turns out to just be the monoidal functors from curly A to BU1. In addition, we need to specify a section of group homomorphism that goes from invertible objects to the group of connected components. So finally, we go even higher to the level of two categories, and then there should be an equivalence of symmetric three categories between 3-vec A, curly A, and 3-vec of its Pontryagin dual. And then we have, so 2-vec now becomes an invertible bimodule between 2-vec A and 2-vec A dual. And we also have equivalentization that enable us to take a finite semi-simple two category with A action to produce a finite semi-simple category with A dual action. And then we can go back also by taking equivalentization of Pontryagin dual. So for outlooks, there are several things to look after this. So we would like to apply this construction to understand the fusion rules of two representations of general two groups, or even better, to understand just the general structure of fusion rules of fusion two categories. And secondly, Pontryagin self-duality and Fourier transform also plays an important role in the study of Tombara-Yamagami categories. It would be interesting to generalize this to two groups, like symmetric two groups, and study the corresponding lattice model and see what kind of physics we get there. And finally, Pontryagin duality and Fourier transform can be defined for non-finite symmetric two groups. So could we find a framework that extends our discussion of fusion two categories that enable us to talk about Pontryagin duality of such non-finite symmetric two groups? So that's the end of my talk, and thanks.
Thank you very much. So is there any question or comment from Nagoya? How about from Zoom?
Yeah, maybe I can ask a few questions. First of all, I would like to thank you, Hao, for this very beautiful talk. So in fact, there's a lot of the things that you've talked about have been something I've been thinking about lately. So, and the first question is, well, you did mention that there's this exchange essentially of the symmetric monoidal structure on the two group itself, and also on the one on modules of vect A, essentially, like two representations of A. Like there's the.
Do you mean? I didn't. Do you mean this one?
Or just the equivalence between 2-rep A with vect A hat.
This one. Okay.
Yeah. So, and as you've mentioned, like there are probably like it's something about half algebras, right? Like I think there are like kind of in a way, like at least for half algebras, there's a duality in this sense, kind of in a very kind of a half, whether I should say like a very bi-algebraic correspondence. which allows me to kind of trade modules of the half algebra with co-modules of the opposite, the dual half algebra. The dual half algebra essentially just flips the algebra and co-algebra structures around. So I would expect something like that to also happen for half categories, right? There should be a way to do that.
So yeah, there are actually many different levels of abstraction. So I want to just make sure. So what kind of Hopf structure are you talking about? Are you talking about Hopf structures on these two categories, or you actually talking about Hopf structures on these like 2-1 categories?
No, just on A, for instance.
Well, A is a group, is a symmetric 2 group. So we cannot talk about Hopf structures.
No, I mean,
there, right?
A is a half category.
Yeah, so here, as I mentioned, you can put different structures on this linearized A, and you have different choice of Hopf structures, indeed. So if the left-hand side is considered to equip this with this pointwise product and its corresponding Hopf category structure, then the right-hand side would have equipped with this convolution product structure. Maybe this is related to what you asked.
Yeah, but like I think there should be, because like if you start with a symmetric monoidal 2 group, then you kind of go through the machinery, and then you notice that the symmetric monoidal structure on one side has to coincide with the other one. That forces you to consider only a specific class of symmetric symmetric 2 groups, right?
Yeah.
But all I'm just saying is that maybe for half categories, there are just way more half categories in which these equivalences, like maybe they're just.
I see. So you are talking about general Hopf categories, not this kind of symmetric and co-symmetric monoidal one.
Exactly.
Oh yeah. Oh, okay, I see. Yeah. For that, I think the situation is different. Yeah, we also have this by analogy with this Hopf algebra in one category. So for commutative and co-commutative Hopf algebra, you have these quantum groups, which behaves kind of orthogonal to what you would expect it to behave for, groups or Lie algebras. So I think, the situation for Hopf categories are not known yet.
Yeah, I don't think it is.
But maybe we should mention here. So there's an ongoing project of Thibaut de Coppet and his collaborators. They're trying to classify fusion 2 categories. So in some sense, if you consider fusion 2 categories with fiber functors, then by Tanaka duality, this is equivalent to consider Hopf monoidal categories. So for their classification of fusion 2 categories turns out to be much more simpler than classification of fusion 1 categories. So there might be a possibility that classification of categories is also not as complicated as that for Hopf algebras.
But I think the fact that their classification is so simple is because they're in the fusion setting. But
okay, yeah. If you drop the fusion, then it's gone very wild, and nobody knows what's going to happen. Yeah.
But yeah, if you don't mind, maybe I can also ask another question, which is more direct. So the Pontryagin dual, like for regular groups, right? The Pontryagin dual is spanned by the irreducible characters. So is there like an analogous statement here?
Oh yeah. So maybe I should go. Yeah. So you see, in the definition of Pontryagin dual, we define it to be category of braided functors. And Previously, Zhihao and Mo Huang and I, we studied these two characters. So our starting point is actually exactly the question you asked. We want to start from two characters of symmetric two groups to construct or find its Pontryagin dual, but we encounter some difficulties, and later we find out it is because they are not the same thing. It's a coincidence that for abelian groups, you have this one-to-one correspondence between irreducible characters and Pontryagin duals. It is no longer true for symmetric two group. It's irreducible two characters. They are Lagrangian algebras. And there are some redundancy on a connected component that it's really not the same thing. And even if you just say, okay, let's just consider like one-dimensional representations of a symmetric two group, right? It's a kind of irreducible representations of two group. And then we should consider monoidal functors from dual, like this curly A to BU1. So by the way, BU1 is just the Picard subgroup of VEC. So it's really, we are considering one-dimensional representations of A. If we replace these braided functors by monoidal functors. But you see, the category of braided functors is not the category of monoidal functors. And we have some reasoning that the other choice is wrong. Because if you just consider category of monoidal functors from curly A to BU1, then it cannot see the braiding on A. So you could have different symmetric two group that give you the same Pontryagin dual, which is not what you want. So
yeah. Okay, yeah. Great. That was very nice. Thank you.
Yeah, thank you. Thanks for the question.
Any other question or comments?
Sorry, I have one question.
Yeah.
So finally, in the final part, you mentioned that Tambara Yamagami something. So
yeah.
Yamagami is Professor Yamagami in Nagoya University previously.
Yes.
So he made such kind of very famous contribution. So I'm very confused because I originally considered that his major is operator algebra, but this one looks like category. So I'm
Yamagami-san's theory is on the tensor category. Yeah, arising from operator algebra.
not operator algebra.
Not necessarily.
Not necessary, including
Not necessary.
operator algebra.
Yeah.
Oh. I checked this one. This one has so relatively many citations. This is very famous work.
Indeed. Yeah.
Oh, I didn't. Sorry.
I
was in my office previously. So.
Yeah, I must admit I don't really know Tambara and Yamagami's work on operator algebras. Although I know that historically they come to these tensor categories maybe by considering from the operator algebra point of view, maybe from subfactor series, such kind of things. But when I learned this concept of Tambara Yamagami, it's already formulated in the pure tensor category, fusion category language. So I don't really know the historical form of it. But yeah, it's kind of deeply related to this fact of some finite cyclic group are Pontryagin dual to itself. And if you're really considering the space of Pontryagin duality, not just the existence of Pontryagin self-duality, then you come into a lot of group cohomological data, you can characterize them, and then it gives rise to this Tambara Yamagami category. Yeah.
Okay, thank you very much. So,
Any other question? Then let's should start again.
Thank you.
And today's session is over. The next day will start on schedule at 9:30 in China and 10:30 in Japan. So see you tomorrow.
thank you very much for attending.